So what on earth is going on with hypothesis testing? Well, we've got this situation, and here we've got a binomially distributed probability, and the probability there is what's in question, not the number of trials, the probability. And somebody is saying that this probability is whatever, and somebody else is saying no, it isn't. Now, this is called the null hypothesis, and this is called the alternative hypothesis. So the alternative hypothesis is the claim that the null hypothesis, which is about what P is wrong. That's what's going on. Then we do the test. Now, what happens when we do the test is that we want to find out, well, okay, let's say it is P. Let's say the probability is a half. Then how weird is it that we got 16 out of 17? That seems pretty weird. How weird would it be to get 3 out of 16? Well, that seems pretty weird too. But what is weird? That's what the question is. And if we get something that is weird, like properly weird, then that allows us to say, do you know what? I think you're right. I think the alternative hypothesis is right. I think the null hypothesis is wrong. I don't think P is this, because if P was that, then why would I get this really weird result? Now, this is not a foolproof way of proving that P is or is not whatever somebody is claiming it is, because if I toss a coin 10 times, I could get 10 heads. It doesn't mean it's a biased coin. Weird can happen. The whole point of the distribution is that all these things are possible. It's just these ones and these ones are really unlikely. So if we get a really unlikely result, then we could say maybe it wasn't that P after all. Maybe it wasn't a fair coin. Maybe it wasn't P as whatever it is we thought it was. Okay. So if we get a weird small, what we're trying to find out is what kind of area of the distribution are we talking about? Are we talking about like this is like the bottom 1% or the bottom 11% or the bottom 30%? So if you've got something weird small, just find out this probability of that shaded region. If it's weird big, find out the probability of that shaded region there. And then there's this thing about one-tail, two-tail. It's really not a big deal. It's literally just what the alternative hypothesis is saying. That's the one-tail or the two-tail. If I say to you, P is not a half, it's way bigger than a half. That's a one-tail test. If I say P is not a half, it's way less than a half. That's a one-tail test. Because I'm just saying, just look down that end. I'm telling you, that's where you're going to get something like down there or up here. If I just say to you, P isn't a half, and I don't claim either way, whether it's big or small, I just say it isn't a half, then that's called a two-tailed test because we need to look in both directions. Now, that doesn't mean we look in both directions. It just means that we're not assuming it's going to go one way or the other. So if I still get something weird small, I'm still going to find this. And if I get weird big, I'm still going to find this. It'll only be one of them that we actually use to find out. The only thing you have to remember is that each test has this alpha level, this significance level, 5% in our case. And that's the definition of weird. So if you're in the top 5%, that's weird. Or if you're in the bottom 5%, that's weird. Now with a two-tailed test, all you have to remember is to split that in half. So if I am doing a two-tailed test and I come out here and I'm in the top 3% of weirdness, okay, top 3%, only 3% of the time would this happen if that was right. Then you look at that and you go, oh, cool, that means, yeah, that's enough, top 3%. Well, no, it isn't, because we were doing a two-tailed test. I didn't claim it was big. I just said it wasn't that. So that means that my 5% is split either end, and actually, in order to be weird officially, I need to be in the top or bottom 2.5%. That's the only thing you need to remember, okay? Right, let's have a go at this actual question, and hopefully you'll see that it's not that difficult. So we're going to start by defining the test statistic. What does that mean? So many words in this. In statistics in general, but also in this particular topic. Well, we need to know what X is. It's really important that we define X. Okay, so let's see what's happening. We've got a day with basically no rain. Okay, so it's the number of days with 0 or trace amounts of rain. And it's always going to be the number of something. So it's the number of days with no or trace amounts of rain. Okay, that's what X is. How is it distributed? Well, each day does or does not have this amount of rain. So it's a binomial distribution, and we've got 21 days, and the probability, well, what we think is the probability, is that it hasn't changed. It's the same as it was before. It's 0.5. So every day is 50-50 chance of no rain. Okay, now let's look at our hypothesis, or hypotheses rather, because there are two hypotheses. The null hypothesis is that nothing has changed. P is a half like it was before. Everything is as it was before. Nothing exciting to see here. The alternative hypothesis, well, let's see. What's somebody claiming? Poppy believes that it's increased. Okay, so she thinks that it's not a half, it's more than a half. She thinks that the likelihood of a rain-free day has increased. We're more likely to have no days with no or trace amounts of rain. So she is saying that P is bigger than a half. That's a one-tailed test. That means that my 5% really truly is 5%. So in order for us to say that Poppy might be right, we're going to reject H0. We don't think P is a half. We think it's bigger than a half. We need to be in the top 5% of weirdness for that to be something that we can conclude. So let's see where we are in the weirdness factor. So test the result. The result that came out, oh no, look, this is not right at all. No, in June, there were 21 days having 0 or trace amounts of rain. X is 21. N is not 21. I wonder if you noticed that while you were watching. N is not 21. N is the number of days. How many days are in June? 30 days in September, April, June, 30. So there's 30 days. And each of those days we're saying, are you or are you not a day with no trace rain? So the result is that we just actually 21. So it seems like she's probably right. It seems like it probably is more than half, because 21, if it was a half, we'd expect 15 and we've got 21, but we need to check. So we need to find out what is 21 and higher. How big is that area? How much of the top weirdness is that? So we've got a big weird, we're going to go to the right, we're going to test this area, we're going to find it. So we want the probability that X is greater than or equal to 21, and that's going to tell us this red area, and we are hoping, or rather Poppy is hoping, that it comes out less than 5%. Right, how are we going to do that? Well, I'm going to write out, because my cumulative tables and my calculator do less than, so I'm just going to jot down my little table, 19, 20, 21, 22. Greater than or equal to 21 is the same as 1 minus less than or equal to 20. Okay, calculator time. So we go menu, statistics, or you can do this very similar set of buttons on the ClassWiz. Distribution is binomial, and I want to do a cumulative distribution. And variable, the lower limit for the binomial is 0, and the upper limit is 20, and the number of trials is 30. That's the number of days, that's n, and the probability, well, at the moment we're still working on it being 0.5. Okay, 0.97. So we're going to do 1 minus 0.97, 861302. So go back into my calculator menu. Blah, blah, blah. Okay, so this is 2.14%. Now, this is where we draw a conclusion. We've got this number. What are we going to conclude? We need to compare it with 5%. And it literally means this. 2.14 is less than 5, right? That's it. So you make the comparison, and then we're going to say that there is sufficient evidence to reject H0, because we're in the top 2%, 2.1% of weirdness here. Only 2% of the time would this happen if that was right. So it probably isn't right. Might be, but we're going to say it probably isn't. There's evidence to suggest that it isn't. So the first thing we say is there is evidence to reject H0. Okay. And then we're going to do a context statement, which is the final mark of this question in the exam. And what you do for that is you basically say what this means and you use the exact words that were in the question. So there is sufficient evidence to, or that, to suggest that, to support Poppy's claim. There is sufficient evidence to support Poppy's claim, but I'm going to say what it is. What is she claiming? The likelihood of a rain-free day has increased. Now, why do students lose marks? They might make a silly mistake like I did there. Some students find the probability that it equals 21. No, we're finding this red area and seeing if it's less than 5%. And then the other thing is doing here, not writing this out and making a mistake going from there to there. So maybe doing less than or equal to 21 or less than 20, something like that. And then the conclusion not being sufficiently written out. These three things, the comparison, the math statement, the context statement, all three of those is part of the conclusion. To get more maths videos from me, subscribe to the Tailored Tutors channel. If you like this video, don't forget to try out my complete A-level course for free in the free trial on the Tailored Tutors website. You can transform your grade in under an hour with my grade transformation playlist, or you can watch this video that has been magically selected just for you from the people at YouTube.